Hello everyone, today I'm going to introduce you to Halley's method, which is used to find the roots of equations. Unlike the other methods, Halley's method not only uses the function or its first derivative, but also the second derivative of the function. While applying this method, there is an important thing to remember. So the different starting points can lead to different roots. So it is very important where you are starting from. So which is basically your first estimation. Let's have a look at the difference between Halley's and the Newton's methods. So what you see on the left side is Newton-Raphson method. It begins at a starting point of x sub 0 and evaluate the function at that point, marked as f of x sub 0. As you can see, there is an orange tangent line. This line is based on the first derivative of the function. Where this tangent intersects the x-axis gives our next estimation, which would be x1. So we keep repeating these steps and the method usually converges very fast. It has quadratic convergence. That means the number of correct digits roughly doubles with each iteration. Let's move on to the Halley's method. So on the right side, we can see the Halley's method. It also starts with x sub 0, so the first estimation. And unlike Newton's method, it also uses the second derivative. So instead of using just a straight line tangent, Halley fits a curve that better follows the actual shape of the function. So we can see that orange tangent lines there actually get the form of the actual function. This curve crosses the x-axis at a point that is typically even closer to the true root. So as a result, Halley's method converges cubically, so tripling the number of correct digits at each step. So both methods aim for the same goal, finding where the function hits 0, but they take different paths. So we can say these two methods are really fast. Okay, so as we discussed in our previous slide, Halley's method is designed to find the roots of function. That is, the values of x that make the function equals to 0. It applies specifically to functions of one real variable that have a continuous second derivative. The method is named after Edmund Halley, the English mathematician and astronomer. He introduced this method as an improvement over Newton's method. Halley's method is part of a broader class of algorithms known as householders' methods, which use derivatives to improve the convergence rate of root finding iterations. Specifically, Halley's method is a third-order method, meaning it has cubic convergence, much faster than the Newton's method, which only has a quadratic convergence. So let's have a look at the formulas of both methods. Newton uses xn, f of xn, and f prime of xn. So basically, we are starting with x sub 0 and using our starting point. When we're substituting this value in our f of x function, we will get f of xn. And then we are substituting same value in the f prime x of x function. Then using that three values, we will get our xn plus 1. Then we substituting xn plus 1 in f of x and f prime of x and the value itself to be able to get the xn plus 2. And it goes so on. Halley's method works in the same way, but additionally it uses the second derivative of the function as well. Okay, let's apply what we've learned about Halley's method to a specific function. Our function is f of x equals to 3x cubed minus 6x minus 9. First thing that we need f prime of x. So we're finding f prime of x, which is equals to 9x squared minus 6. And then for Halley's method, we need the second derivative, which is f double prime of x. That's equals to 18x. Okay, let's move on to how we're gonna apply these methods by using online tools. Now I will demonstrate how these numerical methods can be applied using GeoGebra. Let's start with Halley's method again. So in the very first line, I wrote down my function. And then in the second one, I defined the iteration formula for Halley's method. And I denoted it as h of x. And then I applied direct iteration. My starting point was 1, and I set the number of iterations to 10. And it was pretty enough to observe convergence. As you can see in the matrix M1, the method began converging from the third iteration. And by the fifth iteration, it had reached the accurate root value of approximately 1.8933. Now let's turn to the Newton's method. As you can see in the right side, I similarly defined the Newton iteration formula and labeled it as nr of x, and then followed the same approach. I performed direct iteration starting from 1 and number of iteration is 10. In this case, convergence began around the 6th iteration, and the method reached the same root value of approximately 1.8933 by the 8th iteration. I also want to show you how to apply these methods by using Excel. And I would like to start with showing my macro codes. I described in the macro my f of x and also f prime of x. And obviously I need f double prime of x for my Halley's method. I wrote down my 3 functions. Okay, let's examine the Excel spreadsheet. So first thing that I've done, just writing down my starting point, which was 1, and then substituting this starting point in all of my functions. So f of x, f prime of x, f double prime of x. In this way, I could have tested my macro codes as well. So I saw that everything was working properly. And then I move on to the applying the methods. So to be able to apply the methods, I use 2 columns for each method. So in the column D and G, I aim to see my iterations step by step. And E and I, where I apply the formulas. You can see the formulas in the below. I just put down the formulas if anyone wants to see them as well. So what I've got after these implementations, as expected, just because I tested this before in GeoGebra, Halley's method converged by the 5th iteration, while Newton's method reached convergence in the 8th iteration. To wrap up, let's take a quick look how Newton's and Halley's methods compare in terms of speed, sensitivity to starting point, and ease of use. In terms of speed, obviously Halley's method is faster than Newton's method, as Newton's converges quadratically but Halley's converges cubically, so it can triple the number of correct digits in per step. In terms of sensitivity, just because we starting with the starting point, they both are very sensitive to the starting point. So if we begin too far from the root, they may fail. In terms of ease of use, obviously Newton's method is easier to use just because it only requires 1 derivative of the function. To sum up, Halley's method gives you faster convergence, but at the cost of more work per step. Newton's method is used simpler, more robust, and often just as effective overall. depending on the problem and the available derivatives. Each has its place. Thank you.